During our last lesson, we looked at estimating a population proportion. This one is related to it in that we're still making an estimation of a parameter for a population, but this time we will be looking at the population mean and how we can estimate what that would be. And again, this kind of parallels what we looked at before. The sample mean, which is X bar, is the best point estimate you can use for the population mean mu. The last time we talked about the sample proportion, which is p hat, is the best estimate of the population proportion p. So in both of these cases, for the proportion and the mean, the information you get from your sample is your best place to make your estimate for your population. Now, we do have a couple of cases here. Normally, when you are dealing with a population mean and trying to do an estimate, you do not actually know what the standard deviation is. So this is very common. We don't know the standard deviation. But when we are wanting to do this estimation, we do have to meet a couple of requirements. The sample has to be a simple random sample. By now you're probably getting used to hearing that. Everything that we're dealing with pretty much only works if we have simple random samples. But either one of them or both of the following conditions have to be satisfied. So that's an or, so make sure you recognize that. The population has to be normally distributed, or your sample size has to be greater than 30. You will have some problems that just ask you if you can estimate the population mean here, and if it's not a simple random sample, or you don't have either more than 30 or a normal distribution, you can't use it. We'll also do a confidence interval. And so the confidence interval, and again, we don't know the standard deviation. This is our margin of error. We had a margin of error to calculate last time, but we used a z-score. And this time we're using a t value, and we have not done that before, so that's a little bit different. S is our standard deviation from the sample, and then we have the square root of n. Now, we're going to use degrees of freedom. And so we will have to talk about that later, but the t-distribution is not exactly like the normal distribution. It has a little bit less precision, and that's where this degrees of freedom come in. It changes the shape of a curve a little bit, but just make a note, degrees of freedom for this is n-1. Now this t-value is going to come from the t-distribution. It's called student or student's t-distribution, and it sounds like it's for statistics class people to use, but it's actually kind of an interesting story. The guy who developed this worked for a cannery, and he was not supposed to publish anything that the cannery did not actually sign off on and tell him he could publish. So he just published it under a fake name, and his fake name was the very creative student. I can't remember what he used for his first name, but it'd almost be like us saying John Doe. He was just kind of Joe Student. And so now this became known as student's t-distribution. And we'll be able to find it in the calculator also. And we're also going to use an alpha divided by 2 for the right tail. And again, this will start to make a little bit more sense in a moment. If you had to do a formula, this would be the formula for finding the t-value. Sample mean minus the population mean divided by the standard deviation of the sample divided by the square root of n. This works for all sample sizes n, and so a lot of times this student t-distribution is just called the t-distribution because of the letter it gives us, kind of like a z-value from the normal distribution. But student goes with t. Here's something else you can see just about it. I said it's not exactly normal. We have a green line here that would show the curvature of the normal distribution. The student changes depending on how big your sample size was. And if the sample size is 3, sample size is really small, what happens is on the edges, the graph ends up being taller, but then it is shorter than the normal one in the middle. As we get more and more things included in the study, so as n increases, this hill gets brought up higher in the middle and lower on the edges. And so as n gets bigger, the whole thing starts to look more like the normal one. This little blue note I've put on here is just reminding the mean of this t-distribution is 0, but the standard deviation is bigger than 1. On a normal one, the mean is 0 and standard deviation is 1. But on students, the standard deviation is going to be bigger than 1 because it is more spread out, okay? Not quite as stacked up in the middle. We will need to use, and we did something similar to this last time, we'll need to use a confidence interval or develop a confidence interval for mu. Before we do that, we need to verify our requirements are satisfied. Those two requirements, simple random sample, and it's either normally distributed or n is greater than 30. So that's an or part, but we have two parts. This one is 1, and then one of those. If sigma is unknown, it normally is, use n-1 degrees of freedom. We're going to find our margin of error by taking the critical value times the sample standard deviation over the square root of n. And then we can write our confidence interval in two forms very similar to what we did last time. But now what we will really use is our calculator's t-distribution features. It is important that you remember when you're finding mu and you don't have a standard deviation, you're using the t-distribution. So this is what this is really going to look like for you. Okay, if we have summary statistics for newborn girls, so suppose there was a sample somewhere. It looks to me like this should have been X bar, so let me see if I can draw that bar over it for you. X bar was 30.8. We do know N, we know the sample mean, and we know the sample standard deviation. And we need to conduct a confidence interval of the mean. These pictures are the same, aren't they? Let me just pull this up so we can get this right for you. I am going to do this one just like it says, so I'm going to go to Stats and Test. Stat, go to the right for Test, and then you can see option 8 is a t interval. So you can go down. This is the screen that was missing though. You have a choice here to either enter data or your stats. Data would be like if I actually had all 153 pieces of information to enter in a list. But stats is where I'm going to use my resulting information that they gave me. So I am using stats here, and N was 153. Oh, and I put that in the wrong place, didn't I? That was not clever. X bar was 30.8. Okay. X bar was 30.8. The S, the sample standard deviation, was 6.7. And then N was my 153. Okay, so after this one, this would be the screen that you're going to see after you actually click T interval. And this confidence level depends on what they wanted. So I've got to go check that. Did they want a 90% confidence level? Now see, this one says use a 98% confidence level. So I'm going to change that next one to be 0.98. So that's my 98% confidence level with the three values they gave me in there. Now when I hit calculate, this screen should be what we saw next. Yeah, see that 29.526, 29.526, this is the same thing. This is the result of it, okay? So this actually is the confidence interval. Let me move this calculator out of the way then. What it gives you immediately is the confidence interval. Now the instructions on this particular homework problem said round to 2 decimal places. So I'm just going to round that to 29.5. And then my other number is 32. Oh, it said 2 decimal places. 29.53. That would be 2 decimal places, wouldn't it? And 32.07. Okay, so now let's go back a little bit and look at how this said you could write it. Mu is in between those values, okay? Or you can write those values and put a comma in between with the parentheses, and that's what you see here on the calculator display. So this is one way of writing it, but the other way of writing it is to say that mu is between those two values. So this is one way of writing the answer, and then this is the other way. Of course, it's not rounded right here on your calculator. When we do a confidence interval for the mean, there is a particular statistics phrase that goes with it, and I know you're going to see this somewhere in your homework, but it says the confidence interval methods are robust against departures from normality. This robust against, which kind of means they're really strong in keeping with a departure from normality. In everyday speak, this means they work really well when distributions aren't quite normal. They should be pretty close to normal, but if they're not quite normal, this confidence interval is still going to be really good. So if we've got that t-distribution that isn't quite normal, we're still going to have a really good confidence interval using this method. So it is robust against departures from normality. So this is another type of problem, and we're going to look at the calculator again on the next slide. Hopefully they're all right. But a food safety guideline is that mercury in fish should be below 1 part per million. So that ppm is part per million. Listed below are the amounts of mercury found in tuna sushi sampled at different stores in a major city. Construct a 99% confidence interval estimate of the mean amount of mercury in the population. So first we'll construct the confidence interval, and then does it appear that there's too much mercury in tuna sushi? Okay, one thing to point out here at the beginning is this time I am not given the X bar or S. I'm actually given the data. Okay, so we will need to enter the data. So I think I've got the problem a little bit just kind of carried over to the next page. We're supposed to do a 99% confidence interval. And does it appear there's too much mercury? Now, this is the listing that was on that previous page of the mercuries from the tuna sushi they sampled. I have entered those values in a list. To get to that list, it's stat edit. So I'm not going to retype them all right now. They might still be in here from before. Okay, so if I go to stat edit, I get a listing here, and you can see where I've already typed all those in. This is where I took the screenshot of this picture here. So I just typed all of those in. Now, if you have a lot of numbers and you want to get rid of them, go up to L1, just L1 there, and hit clear. Please don't hit delete. It doesn't totally delete it from your calculator, but it's going to make it where you can't see it anymore. Okay, so just go up and hit clear, and then enter if you need to get rid of a lot of numbers. But I've entered all of those numbers, and that's what you're seeing right here. So that's under stat edit. Now, next thing that happened is once I had those values in, I wanted again to go to my t interval. So I'm going to go to stat test. Now what I didn't write down is actually to get out of this screen, you can hit second mode, that's your quit. So now I'm back to my normal run screen. So under stat, and then I'm going to go over to test. Then I am doing a t interval. And again, it's that t interval. We are estimating a sample mean. So I go to number 8. This time, though, I'm going to use the data that I've entered in my list. So I've got to go over to data and hit enter. And notice it took away those other numbers. That's what's showing up right here. It's asking me where my list is. And so generally, you should have list 1 already there. Sometimes when we do something, you can have a frequency list, but we don't this time. We just had every entry entered once, so that's why it says the frequency is 1. Now, on this problem, they want a 99% confidence interval. So I'm going to go down and make that 99. Okay. So again, all of that should match what I had right over here. And we hit enter. And we get this display, which matches what you're seeing here in the bottom right. So we do get this t interval. So I'm going to write that down a little bit bigger, and we'll round it off some. But then we want to do that interpretation of what this meant. So what we're saying here is that from the samples that were taken at several different stores, this mean, the sample mean was 0.7189 roughly. But what we're saying is that we estimate the population mean with 99% confidence. The actual population mean will be between, I don't think I have how many decimals to go here, so 0.17 and 1.26. So the actual mean is going to be in between those numbers. All right, now does it appear there's too much mercury? Well, let's go back again and see how much mercury it said was okay. It should be below 1. Well, look at this part. This is not saying it has to be below 1. It's a real possibility that the mean is bigger than 1. So at least from this sampling, we would say that yes, there's a good chance. We're not certain, but there could be too much mercury in the sushi because the mean may be greater than 1. So what they would need to do then is either do additional samples. The more samples you include, the better this interval will be. So if they did more sampling, they could narrow that out and say it's okay, or they might, or this lower number might come up and you might find out that it was too high. And it's kind of interesting here if you just look at it, because we only had one value that was higher than 1 in our sample, but yet we cannot be confident that that average will not be higher than 1, or the mean. Okay, so now let's look at where those t values actually come from, because the program we were just using automatically calculated and put those in there. But if you need to actually find the t sub alpha over 2 value, you're going to end up using an inverse t. Kind of like last time we used an inverse norm, now we're using an inverse t. Inverse norm will give you a z value. Inverse t will give you this t value. And what you need to learn really about putting it in there is that whatever that confidence level is, alpha is 1 minus that confidence level. So if you think about this, alpha, 1 minus 0.95 is 0.05. That is alpha. So if you want alpha over 2, all of that has to be divided over 2, and 0.05 divided by 2, alpha over 2 is where that 0.025 is coming in. So you're going to see this number and think, well, 1 minus that number. It's almost like $1 minus 95 cents gives you a nickel. What's half your nickel? 2.5 cents. Okay. Then you're actually putting into your calculator the area that covers the 95% you want, plus this extra little tail, because this calculator is programmed to come in from the left. So I had to take the 0.025 plus the 95, and that's where I got the 0.975 that you can see right here. And that's because that's what's going to take me all the way to this line. And if I only put in the 0.025, I'm going to get this one on the left, which will be negative, and it's going to mark it wrong. Okay, so under second vars, I did inverse t. Inverse t will ask you for an area and degrees of freedom. Now, how did I know degrees of freedom? That's where that earlier slide was that says your degrees of freedom is n minus 1. So we had to use 14 for degrees of freedom, and then I put in the 0.975 for the area. So again, just knowing that that's awfully small on your display, we're going to look at it again on my calculator here, but it's no longer the interval. So I would go to second vars, and then option 4 here is inverse t. You use inverse t when you want to get a t value. The area is your confidence interval plus half of what's left. So since this confidence interval was 95%. I'm going to take 90.95 plus half of that other 5%, and that's where I got 0.975. Degrees of freedom is n-1. So here it said the sample size was 15. That's why I'm putting degrees of freedom 14. That is just kind of an adjustment for how close to normal this particular distribution will be. So we paste and it looks like that. And then you hit enter and we get this 2.1447. So that's our critical value, approximately 2.14. When we find a point estimate and margin of error, you can work backwards. We did the same kind of work on the last lesson, where if you have your point estimate of mu is x bar, you can take your upper confidence limit plus your lower one and divide it by 2, and it will bring you there to the middle. And this x bar is your point estimate for mu. To find the margin of error, you can subtract and divide by 2. So that is the same sort of work as last time, and that has, again, to do with the fact that once you have that confidence interval, if you go from this number to this number, the x bar is in the middle, and then the error is what half of that distance is. So if you really think about it, the distance between the lower limit, I'm going to put LCL, the lower confidence limit, and the upper confidence limit here, that distance between those two values is 2 times E, because you can rearrange this if you just multiply by 2. Now, we sometimes also find a sample size required to estimate a population mean. So we did sample size last time also. Here's kind of an interesting thing. This really is the Z value in here. This is our formula for it. Now, you're probably, again, this is standard deviation, but you may not have standard deviation. It's very normal not to have the actual standard deviation of the population. So you have to use that rule of thumb and just take the range and divide it by 4 if you don't have any other option. And then if you don't get a whole number, since you can't like survey half a person or do half an experiment, you're just going to have to round up. Even, and I don't know that that's really rounding. It's more like go up to the next larger whole number. If you want to estimate, here's another example for that one. And you want to estimate a mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ test if we wanted 95% confidence that the sample mean is within 3 IQ points of the population? That involves then that Z-score. So how do we get that Z-score? Well, we've done that before. That was inverse norm. To get that alpha over 2, I'm going to go second bars, and this is just so I get that Z sub alpha over 2. I need to do inverse norm this time. And here, since this one doesn't just come from the left, I can choose the center and say it's a 95%. So I can do 95% and then say I am looking for the center area. And I get my 2 Z-scores. And what that actually represents then is if I had my thing, one of my Z-scores is over here and one of them's over here, but the critical value is the positive one. So bringing that up, we see that it's 1.96. Now, there might be some of you out there thinking, well, I already knew it was 1.96 because every time we have a 95%, it goes with 1.96. We've had that on a chart before, but it is hard to remember that as you're learning it. So that's the Z value that I'm going to put here for alpha over 2. And then I know that my error has to be within 3. So that is the E part that we're dealing with right here. I didn't put that in here. I'm looking at the sample where I actually pulled this. This was in the textbook. So I wanted to pull it, what it says within your textbook. And this is on page 339. It's example 4 in the textbook if you need to look. But it says you can assume that sigma is 15. That's not true for everything. What I would have expected is actually for them to give me, maybe they tested some kids and then they got a high value and then they got a low value. And it does say within here that whenever they look at IQ scores for people, they have determined that statistics students, you're safe to use this because it's a little bit closer than the general population. So that was given. I need to put that in the problem here. But then that means to apply this, we're going to go in. That should be an N, not just a hoop. N is equal to, and then I had 1.96 times 15 over 3, because remember that's as far off as we want to be, and then squared. And you're going to put all that into the calculator, so let's get that up and do that. So that's where I got my 1.96. I think maybe in front of that I need parentheses first. And then I have 1.96 times 15 over 3, close parentheses, squared. So I just applied that formula. And I get 96.04. But even though this is barely over 96, remember if we have 96 in, we don't quite have enough. So we want to go up to 97. So we said before about round up, although I'm not really sure we should call it rounding. But that's going to go then. This was 96.04, which means we have to have 97 students. So a little formula there you may need. I think that I cannot stress enough though, when you're dealing with this formula, this is a z-score, inverse norm. When we were doing our confidence interval and stuff, we were using a t-score. Now it doesn't happen so very often that you know sigma, but if you do know sigma, don't use t. Let me say that again. If you do know sigma, you don't use t. If you know sigma, you're going to use a normal distribution. One of the things I've told some students before is if in doubt, this sounds a little bit funny, but if in doubt, open up your calculator to see which one you have information for. Under stats, and then I go over to test, and then I have, even though it's under test, it's that z interval like we did before. So z interval. And if you're entering your data or your stats, that's one thing. But let's go over to stats and let me show you what I mean. If you're going to enter stats, you have to know sigma to use this one. If you don't know sigma, you can't use the z interval. By contrast, if we go into that stats test and we look at the t interval again, this one did not ask me for sigma. It just asked me for x bar and s. So sometimes you have to look real closely at the information you have. S is your sample standard deviation, whereas sigma was your population standard deviation. This is still our error. What is the difference between this error and the other one? And this is a z-score. All right, I'm not sure exactly which slide that's on, but if you go back and you look at the margin of error when sigma is unknown, then the error uses a t-score. But here we're going to use a z-score and do a z-interval because we do know sigma. This one is birth weights of girls, but somehow they tell us that sigma is 2.9. So we had some birth weights of newborns earlier. So here it was in our stat test. Then you use the z-interval, and then I entered the information that's given in the problem. I have x bar, I have sigma, I have n, and I have my confidence level. So all that just got entered directly in. And then this is my result. So my confidence interval, I am not, don't forget how to answer the question. I am 95% confident that the true mean lies in this interval. We had some problems with the t-distribution. We had some problems with the z-distribution. It really comes down to this last part. Well, most often this one. First of all, if you don't know sigma, you're definitely using a student's t-distribution. In this one, if you're going to use a normal, you are going to get to use, you're going to have sigma. But you would rarely have sigma in real life, because if we already knew that about the population, we probably wouldn't have to estimate the population mean. So just read real closely. Also, don't forget that they're going to ask you some questions about whether or not you can do this. And so you would have to pay attention to, is it a normal distribution or is n greater than 30? Because here you've got to have one of those two things. It either has to be normal or n has to be greater than 30. Okay? That's also true though down here. It's got to be normal or n has to be greater than 30. So you simply can't estimate the population mean if one of those two things hasn't happened. But if you do need to estimate the mean and you have both of those cases, then you choose between t and z depending on whether or not you know the sigma. Send me any of your Ask the Instructor questions.